Look up at the night sky on a clear evening, and you might just catch a fleeting glimpse of one of the universe's most enigmatic travelers, a comet, slicing silently through the darkness, its glowing tail painting a momentary brushstroke of light. For centuries, these celestial wanderers have captivated our imaginations, symbols of both awe and mystery. But what if they are more than just beautiful spectacles? What if these ancient icy bodies are, in fact, the silent carriers of life itself? This is not science fiction, it's one of the most compelling and profound ideas in modern science, a hypothesis known as panspermia. The notion that life may not have originated on our planet at all, but was instead delivered here from the depths of space, challenges everything we thought we knew about our own beginnings. It reframes comets not as distant, frozen rocks, but as potential cosmic gardeners, sowing the seeds of biology across the cosmos. Imagine for a moment the early Earth, a violent, molten world bombarded by asteroids and comets in its formative years. For a long time, scientists saw these impacts as purely destructive events, wiping the slate clean rather than writing upon it. But what if, hidden within these icy projectiles, were the very building blocks of life? Amino acids, organic molecules, even water ingredients essential for biology as we know it have been discovered on comets and in the dusty tails they leave behind. It's a breathtaking shift in perspective. These celestial nomads, once seen as bringers of chaos, might actually have been the couriers of creation. The possibility that we, and every living thing on this planet, may owe our existence to a comet's long-ago journey is a thought so humbling and wondrous it almost defies belief. In this video, we're setting out on a journey to explore this incredible idea. We'll delve into the science behind panspermia, tracing the evidence that connects these frozen wanderers to the origins of life on Earth. We'll look at cutting-edge research, from the analysis of ancient meteorites to simulations of deep space conditions, asking whether life really could survive the harsh trip between stars. And we'll confront the big questions. If life really did arrive here from elsewhere, what does that mean for our place in the universe? Are we alone or part of a vast, interconnected web of life spanning galaxies? This is a story of curiosity, discovery, and the relentless human drive to understand where we came from, and it's a journey you won't want to miss. So settle in, open your mind, and let's explore one of science's greatest mysteries together. So what exactly is this grand idea, this notion that life could be riding aboard comets? It's a hypothesis with a name that sounds like it's straight out of an epic poem, panspermia. Coming from the Greek words for all and seed, it's the profound theory that life is not confined to our little world, but is a widespread phenomenon throughout the cosmos, and that it can be transported from one world to another. Think of it less like a single spark of life on one planet, and more like a cosmic ecosystem with the building blocks, or even dormant microorganisms hitching rides on natural spacecraft. These aren't deliberate missions, of course, but the random, natural movement of material cast off from one world by an impact, only to eventually, and astonishingly, find a new home on another. It's the universe's ultimate delivery system, operating on a timescale of millions of years. While it feels like a modern, almost futuristic concept, the seed of this idea is incredibly ancient. Over 2,000 years ago, a Greek philosopher named Anaxagoras proposed that the seeds of life were present everywhere in the universe, just waiting for the right conditions to sprout. His vision was remarkably prescient, but like so many revolutionary thoughts, it lay dormant for centuries, overshadowed by other scientific pursuits. It wasn't until the modern era that this idea found its voice again, championed in the 20th century by a pair of brilliant and determined scientists, the astronomer Fred Hoyle and his colleague Chandra Wickramasinghe. They were the ones who looked at the data from space, at the complex organic molecules found in interstellar clouds, and boldly argued that life did not originate on Earth in a secluded pond, but was instead brought here, and that this process of seeding is ongoing. They faced enormous skepticism, as all pioneers do, but they laid the essential groundwork, forcing the scientific community to look up and consider a much, much bigger picture. And in that bigger picture, one type of celestial object emerges as the prime suspect, the most likely vessel for this incredible journey, the comet. Why? Because comets are essentially frozen time capsules from the earliest days of our solar system. They are composed of ice, dust, rock, and a stunningly complex cocktail of organic compounds, everything you'd need to start a biology experiment. More importantly, their journeys are the key. A comet born in the cold, distant reaches of our solar system can be gravitationally nudged inward on a path that might see it collide with a planet like Earth. When it does, it doesn't just deliver a devastating impact, it delivers a payload. It brings water, the universal solvent essential for life. It brings amino acids, the very building blocks of proteins. And it might even bring hardier, more complex precursors to life, all sheltered within its icy interior, protected from the harsh radiation of space during its long voyage. So while asteroids certainly play a role, it's the comets, with their icy preservation and their vast travel routes, that stand out as the universe's most promising couriers, the potential gardeners of the galaxy. To truly grasp their role as potential carriers of life, we need to understand what a comet actually is. The classic description, popularized by astronomer Fred Whipple, is the dirty snowball. And while that's a wonderfully simple image, the reality is far more complex and fascinating. A comet is a dynamic, layered world, a fragile archive from the dawn of our solar system, and its anatomy is key to its potential as a cosmic gardener. At the heart of every comet is its nucleus. This is the solid core, typically just a few miles across, and it's the only permanent part of the comet. Think of it as the command module for the entire spectacular show. This isn't a solid ball of rock. It's a porous, fragile amalgamation of water ice, frozen gases like carbon monoxide and methane, and fine, dark dust laced with incredibly complex organic material. It's this specific recipe of ice, gas, and dust that makes the nucleus so special. When we talk about comets delivering the ingredients for life, this is the treasure chest. Sealed within that deep freeze are the amino acids and other prebiotic molecules that could serve as the raw materials for biology. As a comet's orbit brings it closer to the sun, the heat begins to work its magic on the nucleus. The ices start to sublimate, turning directly from a solid into a gas without becoming a liquid first. This process transforms the inert nucleus into an active comet. The escaping gases puff out, dragging the dust with them, and together they form a giant, fuzzy atmosphere around the nucleus called the coma. This cloud can balloon to be larger than a planet, and it's here, within this temporary atmosphere, that the complex chemistry continues. The sun's ultraviolet radiation bombards these gases, breaking them apart and reassembling them into even more complex molecules, essentially conducting chemistry experiments on a planetary scale. The most famous and visually stunning parts of a comet are, of course, its tails, and a comet typically has two distinct types, both born from the activity of the coma. The first is the dust tail. This is composed of all the tiny particles of dust and rock that were trapped in the ice and are now liberated. This tail is often broad, curved, and brilliantly reflective, shining by reflected sunlight. It's the part we most easily see with the naked eye. The second tail is the ion tail or gas tail. This is made of the gases from the coma that have been ionized by the sun's radiation, becoming electrically charged. The solar wind, a constant stream of charged particles from the sun, then pushes these ions directly away from the sun, forming a long, straight, and often faintly blue-hued tail that can stretch for millions of miles across the solar system. So why does this anatomy matter for the story of life? Because every part plays a role. The nucleus is the protected storage locker, preserving its precious organic cargo for eons in the deep cold of space. The coma is the chemical laboratory where simple molecules can be energized and transformed into more complex ones, and the tails are the distribution system. That magnificent dust tail isn't just for show. It is quite literally seeding the inner solar system with a fine mist of organic rich dust. Some of this dust will eventually drift through Earth's atmosphere, a gentle, continuous rain of potential prebiotic material that has been falling for billions of years. It's a complete, self-contained delivery system, from deep freeze storage to final distribution, all engineered by the simple forces of nature. For generations, the dominant scientific story for the origin of life has centered on our own planet, a concept often poetically called the primordial soup. Picture the early Earth not long after its fiery formation had cooled. Vast, warm, shallow oceans and tidal pools, rich with chemicals washed from the rocks and atmosphere by rain, and energized by lightning strikes, volcanic heat, or the sun's ultraviolet light. In this nutrient-rich broth, the story goes, simple inorganic molecules gradually assembled into more complex organic ones, amino acids, nucleotides, the building blocks of proteins and RNA. Over immense stretches of time, through a process we call abiogenesis, these compounds somehow organize themselves into the first self-replicating structures, taking that monumental leap from non-living chemistry to a living organism. It's a powerful and elegant narrative, one that places the cradle of life firmly here on Earth. However, this terrestrial tale, while compelling, faces some significant scientific hurdles. The most pressing issue is one of time. Geological evidence tells us that life appeared on our planet astonishingly fast. The Earth itself formed around 4.54 billion years ago, and for the first several hundred million years, its surface was a hellish landscape of molten rock and constant, sterilizing impacts from asteroids and comets during a period called the Late Heavy Bombardment. Yet, the oldest fossils we have of microbial mat structures called stromatolites date back to around 3.7 billion years ago. That means life emerged and established itself in a relatively narrow window of perhaps just 500 million years, maybe even less. For many scientists, this timeline feels incredibly tight for the immense complexity of abiogenesis to have occurred entirely from scratch on a newly stabilized world. The second major challenge involves the specific conditions required. The famous Miller-Urey experiment in the 1950s showed that amino acids, the building blocks of proteins, could indeed be formed spontaneously in an atmosphere thought to resemble early Earth. But our understanding of that early atmosphere has changed, and many now believe it was less conducive to those reactions than once thought. Furthermore, creating a building block is one thing. Assembling those blocks into the intricate, self-replicating machinery of a cell in a chaotic, open environment is a problem of an entirely different magnitude. It raises the question, did Earth simply have the perfect conditions against all odds to cook up life in record time? Or could the most complex ingredients have been pre-made elsewhere and simply delivered here, giving that primordial soup a massive head start? This is where the panspermia hypothesis enters, not as a replacement for abiogenesis, but as a potential catalyst for it. Panspermia doesn't necessarily claim that fully formed cells arrived on a comet. Instead, it suggests that comets could have delivered a concentrated payload of the precise organic molecules that are notoriously difficult to form in large quantities on a planetary surface. Imagine the difference between trying to bake a cake from individual atoms of flour, sugar, and eggs versus having all the ingredients pre-measured and delivered to your kitchen. The miraculous assembly into life might still have happened in Earth's oceans, but the most challenging parts of the recipe were provided by the cosmos. This cosmic delivery system elegantly addresses the timing problem. The chemistry to form these complex organic molecules doesn't need to happen in Earth's short, early window. It can happen over millions of years in the vast, cold molecular clouds in space, or on the icy surfaces of comets in the outer solar system, where low temperatures and radiation can actually catalyze the formation of more complex structures. Comets then become the distribution network, transporting these preserved materials across the solar system and seeding young planets like Earth with these precious prebiotic compounds. In this narrative, our planet didn't have to start from absolute zero. It was gifted a starter kit, potentially allowing life to arise much more rapidly once the constant bombardment subsided. It's a shift in perspective from a solitary Earth-bound genesis to a connected, cosmic-scale process, where the possibility of life is woven into the very fabric of the galaxy. So if the chemistry for life can happen right here on Earth, could it also be happening out in the void of space? For a long time, that question belonged firmly in the realm of speculation, but not anymore. The evidence is no longer circumstantial. We now have direct, tangible proof that the cosmos is not just filled with stars and gas, but is in fact teeming with the very organic matter that makes up the foundation of life as we know it. And this discovery fundamentally changes the game, transforming panspermia from a fascinating what-if into a credible how possibly. A huge part of this revolution in understanding comes from a powerful scientific tool called spectroscopy. In simple terms, this technique allows astronomers to analyze the light coming from distant objects, like giant molecular clouds in deep space or the atmospheres of comets, and identify the specific chemical fingerprints of the elements and compounds within them. It's like taking the chemical signature of something billions of miles away without ever having to touch it, and what this tool has revealed is nothing short of staggering. Across our galaxy, in these vast, cold nurseries where new stars and planets are born, we've detected a rich and complex organic chemistry. We're not just talking about simple molecules, we're finding things like alcohols, sugars, and even ring-shaped molecules known as polycyclic aromatic hydrocarbons. The universe, it turns out, isn't just physically vast, it's chemically sophisticated, seemingly pre-programmed to create the ingredients for biology. But spectroscopy, for all its power, is still remote sensing. The real smoking gun, the evidence that moved this from detection to discovery, came from an ambitious mission to literally reach out and grab a piece of a comet. In 1999, NASA launched the Stardust spacecraft on a daring 7-year journey. Its target was a periodic comet named Wild 2. The plan was audacious: to fly through the comet's coma, the cloud of gas and dust surrounding its nucleus, and collect tiny particles from it using a special material called aerogel, a substance so light and porous it could gently capture high-speed dust grains without vaporizing them. Then the spacecraft would stash these precious samples in a capsule and send them hurtling back to Earth for scientists to study. In 2006, that capsule parachuted down onto the Utah desert, and when scientists carefully opened it and began analyzing the minuscule grains of comet dust, they found exactly what they hoped for and more. Among the collection of minerals and ices, they identified the clear and unmistakable signature of glycine. Now, glycine is the simplest amino acid, but it is an amino acid nonetheless, a fundamental building block used by every living organism on Earth to construct proteins. This wasn't a molecule that could have been formed during the intense heat of re-entry, and it had a specific isotopic signature that confirmed its extraterrestrial origin. For the first time in history, we had direct physical proof that a comet, one of those ancient icy wanderers, was carrying a core ingredient for life. This discovery was a monumental validation. It confirmed that the complex organic chemistry we were seeing from afar with our telescopes was real and tangible. Comets weren't just simple dirty snowballs, they were organic factories and delivery trucks rolled into one. Subsequent missions have only built on this incredible finding. The European Space Agency's Rosetta mission, which spent years orbiting and studying comet 67P Churyumov-Gerasimenko, found a whole suite of organic molecules in its atmosphere, including glycine again and even phosphorus, a key element in DNA and cell membranes. Each new piece of data paints the same picture. The raw materials for life are not rare or unique to Earth. They are a common, almost universal byproduct of planet formation, scattered throughout solar systems and embedded within the very comets and asteroids that so frequently collide with young planets. This cosmic abundance of organic material raises a profound question. If comets are indeed these rich repositories of prebiotic ingredients, where did it all come from in the first place? How does the cold, seemingly empty void of space become a nursery for the complex chemistry of life? The answer lies in the very clouds that give birth to stars, and in the gentle, persistent chemistry that occurs on the surfaces of the tiniest dust grains. Long before a star system like our own even exists, its future ingredients are drifting in enormous, diffuse structures known as molecular clouds or dark nebulae. These are not empty voids, they are vast, cold factories of chemistry. Made mostly of hydrogen gas, they are also filled with fine silicate and carbon dust, the soot of long-dead stars. It is on the surfaces of these microscopic dust grains that the story of life's ingredients truly begins. In the freezing temperatures of deep space, just a few degrees above absolute zero, these tiny particles act like minuscule laboratory workbenches. Individual atoms and simple molecules drifting through the cloud, things like carbon, oxygen, and nitrogen, stick to these cold dust grain surfaces. Once anchored, they are no longer just bouncing around randomly. They are held in place, allowing them to shimmy and shift until they find a reaction partner. This process is slow and methodical, operating on timescales of millions of years. A hydrogen atom might land and then be joined by an oxygen atom, forming a hydroxyl molecule. Another hydrogen might arrive, creating a water molecule. Carbon monoxide is a common tenant, and through a series of hydrogen additions, it can be transformed into formaldehyde and then into methanol and even more complex sugars. The incredible lack of heat is actually an advantage here. It prevents these newly formed fragile molecules from immediately breaking apart. But they aren't just sitting in the dark, they are also being constantly zapped by cosmic rays, high-energy radiation pouring through the galaxy. This radiation provides the necessary energy to kickstart reactions that would otherwise be impossible in the deep cold. It's a delicate and beautiful dance. The dust grains provide the stage, the cold provides the stability, and cosmic rays provide the spark. Over eons, this process builds an incredible inventory of complex organic molecules, from simple ices to the precursors of amino acids, all coating these tiny specks of dust like a thin, prebiotic frost. Then gravity begins to stir. A pocket of one of these molecular clouds collapses under its own weight, beginning to form a new star at its center. As it spins and flattens into a protoplanetary disk, all that complex chemistry frozen onto the dust grains gets incorporated into the building blocks of a new solar system. In the warmer inner regions close to the newborn star, these fragile ices mostly evaporate away. But further out, in the cold suburbs beyond what we call the frost line, they remain perfectly preserved. Here, the dust grains coated in organic frost begin to stick together, colliding gently to form ever larger objects, first pebbles, then planetesimals, and eventually the cores of giant planets and the vast population of comets. This is the crucial moment. A comet forming in the outer disk, say in the region of Neptune or in the distant Kuiper belt, is essentially a frozen pile of this primordial, organically rich dust and ice. It is a time capsule preserving the exact conditions and chemistry of that ancient molecular cloud from which our entire solar system was born. When we study a comet today, we are not just looking at a piece of our solar system's history. We are analyzing a sample of the interstellar medium itself, a preserved record of the chemical processes that are common throughout our galaxy. This makes comets natural repositories, or perhaps more accurately, cosmic libraries, cataloging the fundamental organic ingredients that are available to any nascent planetary system. Their journeys inward, then, are not random acts of violence, but could be seen as a delivery of these preserved building blocks to worlds that, like the early Earth, are ready to put them to use. But this entire cosmic delivery scenario hinges on one of the most violent events imaginable, the impact. It's the single greatest objection to the idea of cometary panspermia. How could anything, even the hardiest microbe, possibly survive a collision that releases more energy than all the world's nuclear arsenals combined? The surface of a comet striking Earth would experience temperatures hotter than the Sun and pressures millions of times greater than our atmosphere. It seems like the very definition of sterilizing a sample. For decades, this was the definitive argument that shut down the conversation. But science has a habit of revisiting old assumptions with new data, and what we've discovered in recent years about the tenacity of life is nothing short of revolutionary. The key to unlocking this puzzle wasn't found by looking up at comets, but by looking down at our own planet into its most hostile and unexpected environments. We've discovered entire ecosystems thriving in places we once believed were utterly lifeless. Boiling, acidic hot springs at Yellowstone, the crushing, lightless depths of the ocean trenches, the super salty waters of the Dead Sea, and even the intense radiation surrounding nuclear reactor cores. The organisms that call these places home are called extremophiles, and their existence has completely rewritten our definition of the conditions necessary for life. They prove that biology is not a fragile phenomenon confined to a narrow band of comfort. It is incredibly robust, adaptable, and stubbornly persistent. Among these biological superheroes, one group stands out for its almost mythical resilience: tardigrades, often nicknamed water bears. These microscopic, eight-legged animals are virtually indestructible. When their environment dries up, they enter a state called cryptobiosis, curling into a lifeless-looking barrel known as a tun. In this form, they can withstand the vacuum of space, blistering radiation, and temperatures ranging from near absolute zero to well over 300 degrees Fahrenheit. They can be dehydrated for decades and then spring back to life with just a drop of water. If any earthly organism were to design a perfect passenger for an interstellar comet, it would look an awful lot like a tardigrade in its tun state. But could these or similar organisms actually survive the specific, brutal trauma of an impact event? To answer that, scientists have had to get creative, designing experiments that simulate the incredible forces involved. One of the most famous series of experiments was conducted using a two-stage light gas gun, a device that can fire projectiles at hypervelocity speeds that mimic those of a real asteroid or comet impact. Researchers placed samples of various extremophiles, including the common bacteria Rhodococcus erythropolis and, of course, tardigrades, behind the gun's targets. They then fired tiny pellets at these targets at speeds exceeding 16,000 miles per hour, creating a powerful shockwave that passed through the biological samples. The results were staggering. A significant number of the bacteria and tardigrades not only survived the initial shock but were able to recover, replicate, and continue their lives as if nothing had happened. They had withstood instantaneous pressures up to 1.14 gigapascals, that's over 1 million times Earth's atmospheric pressure at sea level. This is a pressure far greater than any organism would ever experience deep within the ocean or buried underground. It proved conclusively that the sheer force of an impact is not an automatic death sentence for microscopic life, provided it is protected within the impactor. This leads to the second critical part of the survival equation, the comet itself. We must stop thinking of the impactor as a single, homogeneous block. A comet is a porous, loosely packed aggregate of ice and dust, more like a frozen snowdrift than a solid cannonball. When such an object strikes a planet's atmosphere, it often fragments and may even explode in an airburst before it ever reaches the ground. But even if a large piece makes it through, the forces inside the comet are not uniform. While the outer layers are indeed vaporized instantly, creating that immense fireball, material deep within the core can be surprisingly insulated. Think of it like a hard candy with a soft center. The outer shell takes the brunt of the force and heat, protecting the inner material from the extreme conditions. A microbe nestled deep within a crevice in the comet's nucleus could experience a much milder ride, shielded from the worst of the heat by the very ice and rock around it. Furthermore, the angle of impact plays a huge role. A shallow, glancing blow would generate far less heat and shock than a direct head-on collision. And some cometary material doesn't even need to survive a high-velocity impact at all. We know that a continuous, fine rain of cosmic dust, much of it from disintegrating comets, gently settles through our atmosphere every day. This dust is laden with organic compounds and could deliver its potential biological cargo without any fiery drama whatsoever. So when we put all these pieces together, the proven resilience of extremophiles, the experimental data on impact survival, and the protective structure of the comets themselves, the biggest obstacle to panspermia begins to look less like an impenetrable wall and more like a survivable challenge. It transforms the concept from a tantalizing what-if into a plausible how. The universe may not be a gentle place, but life, as we are continually learning, is far tougher than we ever dreamed. Yet for all the compelling evidence supporting the natural, random distribution of life's building blocks, there exists an even more profound and controversial twist on this idea. What if the seeding of our planet was not a matter of chance, but of choice? This is the realm of directed panspermia, a hypothesis that pushes the boundaries of science and ventures into the territory of science fiction, suggesting that life on Earth may have been an intentional act, a biological message in a bottle sent across the cosmos by an intelligent, advanced civilization. The concept was first seriously proposed in the 1970s by none other than Francis Crick, the Nobel Prize-winning co-discoverer of the structure of DNA. Crick, alongside chemist Leslie Orgel, wasn't content with the unexplained leap from complex organic molecules to the first self-replicating life form. They argued that the origin of that first primitive cell was statistically so improbable in the available time that it pointed toward an alternative explanation. Their radical suggestion was that a civilization, perhaps facing its own imminent extinction, could have deliberately chosen to propagate life by sending out microbial spores on shielded spacecraft to fertile planets. In this view, comets aren't the delivery vehicles, incredibly advanced technology is. The arguments in favor of this idea are as fascinating as they are speculative. Proponents point to the universality of the genetic code. Every living thing on Earth, from the smallest bacterium to the largest blue whale, uses the same fundamental biochemical language to translate DNA into protein. This shared rulebook could be seen as a powerful signature of a common, perhaps even designed, origin. Furthermore, certain metal elements like molybdenum, which play a crucial role in many enzymatic reactions in terrestrial life, are relatively rare on Earth's surface. Could this indicate that our biology was optimized for a different, unknown environment and then transplanted here? For advocates, these are not mere coincidences but potential clues in a cosmic archaeological dig. Naturally, the theory faces immense and valid scientific criticism. The foremost objection is its reliance on an unproven premise, the existence of another technological civilization. It essentially substitutes one mystery, the origin of life, with another, arguably even larger one. Critics, often invoking Occam's razor, argue that it's far more parsimonious to assume a natural, albeit not yet fully understood, process for abiogenesis on Earth than to invoke an entire unseen civilization. There's also the staggering technical challenge. Even if such a civilization existed, launching a mission that could survive millions of years in interstellar space and successfully land on a specific target planet stretches our understanding of physics and engineering to its absolute limit. But perhaps the most enduring impact of directed panspermia is not its scientific validity, but its profound philosophical implications. It forces us to confront our place in the universe in a completely new way. If true, it would mean that every human, every plant, every creature is part of a lineage that extends beyond our star, making us all citizens of the galaxy. It reframes our entire evolutionary history, from a solitary tree of life on an isolated world to a single branch on a vast cosmic family tree. It raises unsettling questions about purpose and destiny. Are we an experiment? Are we descendants? Or are we simply the accidental beneficiaries of a project we can scarcely comprehend? This idea doesn't provide answers so much as it opens a door to a universe filled with possibilities far stranger and more wonderful than we had ever imagined. But the journey of a life-bearing comet doesn't have to end at the borders of our own solar system. While traveling from the Kuiper belt to Earth is an epic voyage in its own right, it's a relatively short trip on the cosmic scale. The truly mind-bending version of this idea, the one that truly opens up the galaxy, is known as interstellar panspermia. This is the hypothesis that life could not only hop between planets, but between entire star systems, turning the entire Milky Way into a single, interconnected biological network. The mechanisms for such an incredible journey are just as real as the comets themselves, though the scales involved are almost incomprehensible. For a piece of a planet or a life-bearing comet to escape its native star system and reach another, two immense challenges must be overcome: the initial ejection and the interstellar voyage itself. The first challenge, ejection, requires an almost unimaginable amount of energy. A planet's gravity is a powerful anchor, and breaking free from it to achieve solar system escape velocity is no small feat. The most likely catalyst for such a dramatic event is a close gravitational encounter. In the chaotic early days of a star system, the orbits of large planets can be unstable. A gravitational slingshot from a gas giant like Jupiter could easily fling a smaller object out of the solar system entirely, like a stone from a sling. An even more powerful driver could be a near miss with another star. While the distances between stars are vast, our Sun is part of a moving cluster, and in its youth, it likely had many stellar siblings much closer than any star is today. A passing star could gravitationally perturb the outer cloud of comets in a system, the Oort cloud, sending a shower of them hurtling into interstellar space. The most violent ejection mechanism of all would be a nearby supernova. The explosive death of a massive star could blast material right off the surface of a nearby planet or rip entire comets from their orbits, propelling them outward with tremendous force. Once free from its stellar parent, the object becomes a rogue, a lone traveler in the dark between stars. This is where the second challenge begins: survival on an interstellar timescale. The distances here are not measured in millions of miles, but in light years. Even at the incredible speeds these objects can achieve, a journey to the nearest star system, Proxima Centauri, would take tens of thousands of years. A trip across the galaxy would take millions, if not hundreds of millions of years. For any potential biological passenger, this is an eternity spent in the most extreme environment imaginable. The near-total vacuum of space, with temperatures just a few degrees above absolute zero and a constant bombardment of cosmic radiation. This is why the evidence for the durability of extremophiles and tardigrades is so critical. A microorganism in a dormant, cryptobiotic state could, in theory, enter a state of suspended animation, its metabolism shut down completely, allowing it to weather the eons in a kind of biological stasis. It would need to be buried deep within its rocky or icy vessel, shielded from the worst of the radiation, but as our experiments have shown, such survival is not outside the realm of possibility. The final act of this epic drama is capture. After its multi-million-year journey, the interstellar traveler must somehow be caught by another star system. This is arguably the most improbable step in the entire process. Space is overwhelmingly empty. The chance of a specific tiny object randomly colliding with a specific planet in another system is astronomically low. However, we must think in terms of sheer volume and time. Our galaxy contains hundreds of billions of stars, each with its own potential cloud of comets and planets. Over the galaxy's 13.6 billion-year history, countless trillions of such objects have been ejected. While the odds for any single one are vanishingly small, the law of truly large numbers suggests that some successful transfers are not only possible but statistically likely. A rogue comet could be gravitationally captured by the Oort cloud of a passing star, eventually being nudged inward over millions of years to fall into the inner planetary system, where it might collide with a young, habitable world, just as comets did in our own early solar system. This process wouldn't be efficient or fast, but on a galactic scale, it provides a slow, steady drizzle of potential biological material across the cosmos, a gentle exchange of cosmic ingredients between stellar neighbors. This idea suggests that life, once it arises anywhere, might have a pathway to spread, making the galaxy not a collection of isolated islands, but a single, vast ecosystem, connected by these incredibly patient, icy messengers. To understand the potential role of comets as cosmic gardeners, we must travel back to a pivotal chapter in our planet's deepest history, a time of both unimaginable destruction and, paradoxically, incredible possibility. This was the era of the late Heavy Bombardment, a period roughly between 4.1 and 3.8 billion years ago. Picture the solar system not as the relatively orderly place it is today, but as a chaotic cosmic shooting gallery. The giant planets were still migrating, their immense gravitational pulls acting like wrecking balls, destabilizing countless asteroids and comets in the outer solar system and flinging them inward. For hundreds of millions of years, Earth and its neighboring worlds were subjected to a relentless, terrifying rain of impacts. The surface of our young planet would have been a constantly churning hellscape of molten rock and titanic explosions, with the sky perpetually glowing from the fiery trails of incoming projectiles. The traditional scientific view of this period was understandably grim. It was seen as a cosmic catastrophe, a final, violent act of planetary formation that would have repeatedly sterilized the Earth's surface. Any tentative beginnings of chemistry that might have been leaning toward life would have been utterly vaporized by impacts that created vast oceans of magma and boiled away any existing water. This perspective painted the bombardment as a definitive barrier, a reason why life could not have possibly begun until after this celestial onslaught had finally subsided. The clock for the origin of life, in this view, only started ticking after the solar system had settled down. But what if we've been looking at this entire epoch through the wrong lens? What if this violent rain wasn't just a destructive force, but also a creative one? This is where the narrative takes a fascinating turn. Instead of seeing comets and asteroids solely as agents of annihilation, we can also view them as celestial supply ships. Every one of those impacts, while devastating on a local scale, was also a delivery. They were bringing vast quantities of two things the early Earth desperately needed: water and complex organic molecules. We now know that comets are rich in water ice, and the constant pummeling could have been the primary mechanism that filled our oceans. More importantly, they were also depositing their cargo of prebiotic material, the amino acids, sugars, and other organic compounds we've detected on them, directly onto the planet's surface. This doesn't mean life had to be present on those first impactors. The more compelling idea is that the bombardment was essentially stocking the pantry. It was providing the raw ingredients in massive, concentrated quantities. Think of it as a cosmic bombardment of fertilizer. The energy from the impacts themselves could have also played a role. churning the planet's crust and creating vast networks of hydrothermal vent systems deep underground or in the newly forming oceans. These warm, mineral-rich environments, safe from the sterilizing effects of impacts on the surface, could have served as the perfect protected laboratories where those delivered organic molecules could mix, interact, and begin their slow, intricate dance toward greater complexity. The timeline itself becomes a powerful piece of evidence for this more optimistic view. The late heavy bombardment didn't end with a clean cutoff, it gradually tapered off. The earliest evidence we have for life on Earth, in the form of isotopic signatures in ancient zircon crystals, dates to around 4.1 billion years ago, right in the middle of this violent period. This suggests that life may not have been waiting for a quiet, peaceful time to emerge. It may have been seizing opportunities amidst the chaos, finding refuge in subsurface aquifers or deep ocean vents, using the very materials that the impacts were providing. The fiery welcome of the late heavy bombardment may not have been an obstacle to life after all, but rather its chaotic, violent, and incredibly fruitful birth canal. The European Space Agency's Rosetta mission stands as one of the most ambitious and revealing voyages of discovery in the history of space exploration. Designed not just to fly by a comet but to truly get to know one, its goal was audacious: to rendezvous with a comet, orbit it for nearly 2 years as it journeyed around the Sun, and deploy a lander to its surface. The target was Comet 67P/Churyumov-Gerasimen Co., a 4.5 billion-year-old time capsule from the dawn of our solar system. What Rosetta found there didn't just meet expectations. It completely revolutionized our understanding of these icy wanderers and delivered the most powerful, direct case for their role as carriers of life's essential ingredients. After a decade-long journey through the solar system, the Rosetta spacecraft arrived at Comet 67P in August 2014. The first surprise was the comet's peculiar shape. Rather than a simple round ball, it was revealed as a breathtaking rubber duck-shaped object, likely formed from 2 separate bodies that had gently fused together in the early solar system. This strange structure hinted at a gentle, low-speed formation process, perfect for preserving fragile ancient materials. As Rosetta began its intricate orbital dance, its suite of powerful instruments started sniffing the comet's coma, analyzing the gases and dust boiling off its surface as the sun's heat warmed it. The results were staggering. The comet's coma was not just simple water vapor and carbon dioxide. It was a chemical treasure trove. Rosetta's Rossina mass spectrometer detected a richer and more complex array of volatile molecules than anyone had predicted. It found nitrogen-bearing compounds like ammonia and hydrogen cyanide, a key precursor to amino acids. It discovered sulfurous molecules and an astonishing variety of carbon-based organics, including the simple sugar glycolaldehyde, which is involved in the formation of RNA. But 2 discoveries in particular sent shockwaves through the scientific community and directly supercharged the panspermia debate. The first was the completely unexpected detection of molecular oxygen. Oxygen is a highly reactive gas. It readily binds with other elements, so finding large quantities of it just floating around in the comet's atmosphere was a major puzzle. Scientists had assumed any primordial oxygen would have long since combined with hydrogen to form water. Its presence suggested that the oxygen had been trapped in the ice since the very formation of the comet and had survived for billions of years untouched. This had huge implications not just for comet chemistry, but for the chemistry of the early solar system and the type of raw materials that would have been delivered to early Earth. The second landmark find was phosphorus. On Earth, phosphorus is absolutely essential for life. It forms the backbone of DNA and RNA molecules, and it is a critical component of ATP, the universal energy currency of every living cell. Yet on our planet, phosphorus is often locked away in minerals, making it relatively inaccessible. For years, scientists had wondered how this crucial element became available for the first life forms. Rosetta provided a stunning answer. Comets could have been the delivery system. The discovery of phosphorus gas in the coma of Comet 67P marked the first time this vital element had been found in a form that could be easily utilized by living organisms, suggesting that cometary impacts could have seeded young planets with this biological keystone. The mission's crowning achievement was the deployment of the Philae lander. Although its harpoon system failed to fire and it came to rest in a shadowy crevice, limiting its operational time, the little lander still managed to conduct science. Most significantly, its Ptolemy and Cossack instruments sniffed the comet's surface and detected 16 organic compounds, 4 of which, including acetamide, acetone, and methyl isocyanate, were found for the very first time on a comet. These are precisely the sorts of molecules that can undergo further reactions to form amino acids and other crucial prebiotic compounds. Together, the findings from Rosetta and Philae painted a definitive portrait of Comet 67P, not as a simple dirty snowball, but as a dynamic, complex, and incredibly organic, rich world. It provided the most compelling evidence to date that comets are not just carriers of water, but of the entire starter kit for life: the carbon frameworks, the nitrogenous compounds, the precious phosphorus, and even the unexpected chemical energy sources like molecular oxygen. This mission moved the conversation from theoretical speculation to hard, observational fact. We no longer have to wonder if comets contain the ingredients for life. We have now visited one, and we know that they do. Yet for all the organic richness comets provide, a living world needs something even more fundamental: liquid water. It's the universal solvent, the essential medium in which the chemistry of life can unfold. And here we confront one of the great mysteries of our own planet's history. The early Earth, fresh from its violent formation, was likely a hot, dry, and molten world. Any original water it might have held would have been boiled away into space by the intense heat and the constant pummeling from impacts. So where did our vast, life-giving oceans come from? The evidence increasingly points to the skies, suggesting that our water, like the ingredients for life, was a delivery from beyond. Comets, those massive, dirty icebergs swinging in from the outer solar system, have long been the prime suspects in this celestial heist. The logic seems undeniable. Comets are, by definition, mostly water ice. During the late Heavy Bombardment, countless billions of them would have rained down upon the young Earth. Each impact would have vaporized on arrival, releasing its frozen cargo as steam into the primordial atmosphere. Over millions of years, as the planet finally cooled, this steam would have condensed and fallen as rain, gradually filling the great basins to create the first oceans. It's a beautifully simple and elegant theory, painting comets as the benevolent water bearers for a parched world. For decades, this was the prevailing scientific story, a cornerstone of the panspermia hypothesis. But then, we developed the tools to test it, and the story got a lot more complicated. The key to unlocking the mystery of Earth's water lies in a subtle but powerful chemical fingerprint: the ratio of hydrogen to its heavier isotope, deuterium. Think of it like a cosmic barcode. Water, or H2O, is made of 2 hydrogen atoms and 1 oxygen atom. But occasionally, one of those standard hydrogen atoms is replaced by a deuterium atom, creating what's called heavy water. The ratio of normal hydrogen to deuterium in a water sample is a powerful tracer of its origin and history. It's affected by the temperature at which the water formed, the environmental conditions it was exposed to, and the specific region of the solar system it came from. By measuring the deuterium to hydrogen ratio, or D/H ratio, in Earth's oceans, and then comparing it to the ratios found in different celestial objects, we can look for a match, a likely source for our water. When scientists first turned their spectrometers toward the most famous comet of all, Halley's Comet, during its 1986 apparition, the results were shocking. The D/H ratio in Halley's water was about twice as high as the ratio found in Earth's oceans. This was a major problem. If comets like Halley, which come from the distant Oort cloud, were the primary delivery method for our water, then our oceans should have that same high deuterium signature. But they don't. This finding threw a massive wrench into the pure cometary delivery model and forced scientists to look elsewhere. For a time, asteroids seemed to be the new heroes. Meteorites known as carbonaceous chondrites, which originate in the asteroid belt, were found to have a D/H ratio much closer to Earth's. The narrative shifted. Perhaps it was asteroids, not comets, that filled our oceans. But the universe, as it often does, had a surprise in store. In 2011, the Herschel Space Observatory turned its gaze to a very different kind of comet, Hartley 2. Unlike Halley, which is a long-period comet from the Oort cloud, Hartley 2 is a Jupiter family comet, meaning its orbit is controlled by Jupiter's gravity, and it's believed to originate from the much closer Kuiper belt. When Herschel measured Hartley 2 water, the result was a revelation. Its D/H ratio was almost a perfect match for Earth's oceans. Suddenly, the picture became far more nuanced. It wasn't that comets were ruled out, it was that not all comets are created equal. The origin of a comet, it seems, is everything. Oort cloud comets like Halley, which formed in the frigid, outermost reaches of the solar system, have a distinctly different deuterium signature than those like Hartley 2 that formed a bit closer to the Sun in the Kuiper belt. This discovery suggests a more complex and likely mixed origin for Earth's water. The current best theory is that our oceans are the result of a diverse delivery service. Some of our water probably did come from asteroids, which were plentiful in the inner solar system, but a significant portion almost certainly came from a specific family of comets, those that formed in the same general region as Hartley 2. The early Earth was likely bombarded by objects from both populations, and our oceans are the blended cocktail of all their contributions. This doesn't diminish the role of comets, it refines it. It tells us that the specific conditions in the Kuiper belt region were just right to produce water with an Earth-like composition, and that gravitational interactions were able to successfully ferry that water inward to our waiting planet. This makes the story of our water not a simple tale of a single source, but a rich narrative of cosmic connection, with our world serving as the grateful recipient of gifts from across the entire solar system. This complex interplay between creation and destruction, between a violent rain of impacts and the gentle seeding of a new world, forces us to confront a profound and practical question. If we are not alone, and if life can indeed travel between worlds, how would we even know? How do we go about looking for it? The quest to answer this very question led to one of the most intriguing and controversial chapters in the history of space exploration, the Viking missions to Mars. In the 1970s, NASA embarked on an unprecedented endeavor, sending two robotic landers, Viking 1 and Viking 2, to the surface of the Red Planet. Their primary objective was not just to take pictures and measure the weather, it was to answer humanity's oldest question in a definitive way. They were designed to search for life. Each Viking lander was a complete biological laboratory, equipped with 3 ingenious experiments crafted to detect metabolic activity in the Martian soil. The labeled release experiment added a nutrient soup containing radioactive carbon to a soil sample, on the theory that any microorganisms present would consume the food and release radioactive gas as waste, which the instrument could then detect. The pyrolytic release experiment sought to simulate photosynthesis by offering radioactive carbon dioxide and carbon monoxide to a soil sample under a lamp, hoping Martian microbes would incorporate the carbon into organic material. The gas exchange experiment moistened a soil sample with a nutrient broth and then monitored the air above it for signs that gases were being consumed or produced by living organisms. The scientific community held its breath, waiting for a clear result. What they got was anything but clear. Astoundingly, the labeled release experiment came back positive. It detected a burst of radioactive gas, just as it would if life were present. For a moment, it seemed we had found our answer, but the celebration was short-lived. The other experiments provided confounding data. The pyrolytic release experiment showed a very faint positive signal, while the gas exchange experiment detected chemical activity, but not of a type that was easily explained by biology. The most decisive blow, however, came from another instrument altogether, the gas chromatograph mass spectrometer, which was designed to directly look for organic molecules, the very building blocks of life. It found nothing, not a trace. It was this stark contradiction that created the Viking enigma. How could there be life metabolizing nutrients without any organic material present for that life to be made of? The prevailing scientific consensus that eventually emerged was that the positive results were not evidence of life, but of a strange and unexpected chemistry in the Martian soil. The leading theory points to the presence of perchlorates, highly reactive salts that are now known to be widespread on Mars. When the Viking experiments added water and nutrients to the soil, these perchlorates could have broken down the organic compounds, effectively destroying them before the GCMS could find them, while simultaneously producing the bursts of gas that mimicked biological activity. In essence, the Martian soil itself was chemically breathing, fooling our most sophisticated life detection experiments by acting in a way that was eerily lifelike. The lessons from Viking were humbling and profound. First, it taught us that detecting life is incredibly difficult, especially from hundreds of millions of miles away. Our experiments are based on our assumptions of how life should behave, assumptions built entirely on the single example of life on Earth. We were looking for a reflection of ourselves, and Martian chemistry gave us a funhouse mirror instead. Second, and perhaps more critically for the idea of panspermia, Viking brought the concept of planetary protection sharply into focus. The missions were sterilized with immense care before launch to prevent forward contamination, the risk that we might accidentally seed Mars with hardy Earth microbes, forever confusing any future search for indigenous Martian life and potentially irrevocably altering another world's ecosystem. The terrifying prospect is that a single resilient bacterium hitching a ride on a spacecraft could survive the journey and find a new home, beginning a process of interplanetary seeding initiated not by nature but by us. This concern works in both directions. The same protocols are essential for missions designed to return samples to Earth from places like Mars or asteroids to prevent back contamination. The hypothetical risk of introducing an extraterrestrial organism to our biosphere with unknown consequences. While the chances of a Martian microbe being able to infect terrestrial life are considered extremely low, the potential stakes are unimaginably high, warranting the utmost caution. The entire framework of planetary protection is built on the foundational principle that the exchange of biological material between worlds is a real possibility. It is a stunning admission. Our space agencies officially operate on the assumption that panspermia, whether natural or human-induced, is a credible enough threat that we must spend millions of dollars and immense effort to guard against it. The ghosts of the Viking results, those ambiguous signals from a rusty red desert, continue to shape how we explore the cosmos, reminding us that the universe is far more chemically clever than we ever anticipated, and that we bear a profound responsibility as we take our first tentative steps into the great cosmic ocean. To truly grasp whether life could endure an epic journey across the cosmos, we don't need to look to the stars. We can look right here on Earth into its most hostile and unexpected environments. This investigation leads us directly to the extraordinary world of extremophiles, organisms that don't merely survive but actually thrive in conditions that would be instantly lethal to almost everything else. These biological superstars are the ultimate test subjects, living proof that the boundaries for life are far, far wider than we ever imagined, and they provide the most compelling evidence that a microbe could indeed survive a multi-million-year voyage inside a comet. Consider the scalding, acidic hot springs of Yellowstone National Park, where water boils at the surface and the pH is akin to battery acid. Here, microbes called thermophiles and acidophiles flourish, their specialized enzymes and protective cellular membranes perfectly adapted to an environment that would instantly cook and dissolve most other cells. Then there are the barophiles, organisms that call the deep ocean trenches their home, thriving under pressures 1,000 times greater than at sea level in perpetual darkness. In the frozen deserts of Antarctica, cryptandoliths live a slow-motion existence, hidden within the microscopic pores of rocks, surviving on traces of water and the faintest trickle of sunlight. Perhaps most astonishing are the organisms that have evolved to withstand one of space's greatest hazards, radiation. The bacterium Deinococcus radiodurans is the reigning champion in this category, capable of surviving radiation doses thousands of times higher than what would kill a human. This incredible microbe doesn't avoid radiation damage, it has a miraculous ability to repair it. When its DNA is shattered into hundreds of pieces by intense radiation, Deinococcus radiodurans can swiftly and accurately reassemble its entire genome, effectively putting itself back together again. This isn't just resilience, it's a near superpower, a biological cheat code for surviving in the most punishing environments imaginable. The existence of such organisms completely shatters our preconceived notions of what life requires. It demonstrates that biology is not a fragile flame, needing a perfect, narrow band of conditions to exist. Instead, it is a pervasive and stubborn force, capable of adapting to exploit even the most extreme niches. This radical adaptability is the cornerstone of the argument for panspermia. If a microbe can happily live in a boiling acid bath or reassemble its shattered DNA, then the challenges of space, the vacuum, the cold, the radiation begin to look less like absolute barriers and more like just another set of problems for which evolution has already found a solution. These extremophiles provide the crucial how to the panspermia hypothesis, offering tangible, Earth-based models for the kind of passengers that could potentially hitch a ride on a comet. Their relevance becomes stunningly clear when we consider the specific, brutal trauma of an impact event. For decades, the immense forces involved in a comet striking a planet were seen as the definitive argument against panspermia. How could anything survive a collision that releases more energy than all the world's nuclear arsenals combined? To answer that, scientists designed ingenious experiments to simulate these incredible forces. Using a two-stage light gas gun, a device that can fire projectiles at hypervelocities, researchers tested the limits of these biological superheroes. They placed samples of bacteria like Rhodococcus erythropolis and the legendary tardigrades behind the gun's targets and fired tiny pellets at speeds exceeding 16,000 miles per hour, creating a powerful shockwave that passed through the biological samples. The results were nothing short of revolutionary. A significant number of these organisms not only survived the initial shock but were able to recover, replicate, and continue their lives as if nothing had happened. They had withstood instantaneous pressures over 1 million times Earth's atmospheric pressure. This proved conclusively that the sheer force of an impact is not an automatic death sentence for microscopic life, provided it is protected within the impactor. This leads to the second critical part of the survival equation, the structure of the comet itself. A comet is not a solid cannonball, it's a porous, loosely packed aggregate of ice and dust, more like a frozen snowdrift. While the outer layers are vaporized instantly upon impact, creating that immense fireball, material deep within the core can be surprisingly insulated. A microbe nestled deep within a crevice in the comet's nucleus, perhaps in a dormant state, could be shielded from the worst of the heat and shock by the very ice and rock around it, experiencing a much milder ride to the surface of a new world. When we put all these pieces together, the proven resilience of extremophiles, the experimental data on impact survival, and the protective structure of the comets themselves, the biggest obstacle to panspermia, begins to look less like an impenetrable wall and more like a survivable challenge. Extremophiles are not just a scientific curiosity. They are the living blueprint, the empirical evidence that the universe may be far more habitable and life far more tenacious than we ever dared to dream. While comets have rightfully captured our imagination as potential life-bearers, their celestial cousins, the asteroids, present a powerful and compelling alternative narrative in the story of panspermia. These rocky bodies, which primarily orbit in the belt between Mars and Jupiter, offer a different set of advantages and challenges as vectors for spreading life's ingredients across the solar system. The key to understanding their role lies not in their dazzling appearance, but in their composition and their history. Unlike the icy, volatile, rich comets that formed in the deep freeze beyond the frost line, most asteroids are thought to have coalesced much closer to the Sun, in warmer regions where ices could not remain stable. This gives them a fundamentally different character. They are largely rocky and metallic worlds, more akin to the terrestrial planets than to the dirty snowballs of the outer solar system. Yet to dismiss them as barren rocks would be a profound mistake. A specific class of asteroids, known as carbonaceous asteroids, are among the most primitive and chemically rich objects we have ever studied. They are the parent bodies of carbonaceous chondrite meteorites, which have been raining down on Earth for billions of years. When we analyze these space rocks in our laboratories, the results are astonishing. They are not simple stones, they are complex chemical reservoirs packed with a stunning array of organic compounds. We have found amino acids, the building blocks of proteins, within them. We've discovered nucleobases, the informational components of DNA and RNA. We've even identified sugars and complex hydrocarbons. This rich organic inventory is locked within a clay-rich matrix that also contains something even more crucial: water, not as free-flowing liquid but bound within hydrated minerals. This combination makes carbonaceous asteroids incredibly potent delivery vehicles, carrying both the molecular instructions for life and the water required to activate them. This leads us to the great debate, which makes the better cosmic gardener, the asteroid or the comet. The argument for asteroids hinges on their gentler delivery mechanism and their proven record. An asteroid impact, while still cataclysmic, is often a more straightforward event than a comet strike. Comets, with their high volatile content, can experience violent outgassing and fragmentation as they approach the Sun, which might compromise any delicate biological cargo. Asteroids, being more structurally solid, might offer a more stable and protected environment for hardy microbes during their journey. Furthermore, the evidence for their organic delivery is literally in our hands. We have countless carbonaceous chondrite meteorites in our collections that arrived on Earth without being completely sterilized, proving that complex organics can survive the atmospheric entry process. Comets, on the other hand, boast their own impressive resume. Their main advantage is sheer quantity and preservation. Comets are thought to contain a higher percentage of life's essential volatiles like water, carbon dioxide, and methane. More importantly, because they formed in the perpetual deep freeze of the outer solar system, their organic material has been kept in a state of cosmic refrigeration for over 4.5 billion years, potentially preserving it in a more pristine and unaltered state than the material on asteroids, which may have been subject to more heating and alteration during the solar system's violent early days. Their dramatic journeys from the outer solar system also mean they have the kinetic energy to deliver their payloads to a wider range of worlds. Perhaps the most insightful perspective is not to see them as rivals, but as partners in a grand cosmic enterprise. The early inner solar system was likely bombarded by both populations in a relentless downpour. Asteroids originating from closer in might have provided the bulk of the material that formed the Earth's very crust and a significant portion of its water, delivered gently within their clay minerals. Comets arriving from the distant frontiers could have provided supplemental volatile-rich material and a different, perhaps more diverse, suite of complex organic molecules in dramatic high-energy impacts. Together, this mixed bombardment would have created a rich and varied prebiotic environment on the early Earth, offering countless chemical pathways and opportunities for life to emerge. The story of our origins may not be a simple choice between a comet or an asteroid, but a complex tapestry woven from the contributions of both of these ancient messengers from the dawn of time. This sprawling cosmic perspective, where life might potentially hop from star to star, forces us to confront one of astronomy's most famous and haunting questions. If the universe is so vast and ancient, and the ingredients for life so seemingly abundant, then where is everybody? This is the essence of the Fermi Paradox, the startling contradiction between the high probability of extraterrestrial civilizations and the utter lack of any observable evidence for them. If panspermia is a viable mechanism, effectively turning the galaxy into a network of interconnected biological systems, then this silence becomes even more profound and perplexing. It suggests that while the raw materials for life might be common, the journey from those materials to an intelligent, technologically advanced civilization is fraught with obstacles we are only beginning to understand. One of the most compelling frameworks for addressing this paradox is the Great Filter hypothesis. This idea proposes that there exists somewhere along the path from non-living matter to spacefaring civilization at least one nearly insurmountable barrier, an evolutionary bottleneck that prevents life from progressing beyond a certain point. The terrifying implication is that the reason the galaxy seems empty is that every other civilization has hit this filter and been erased from the cosmic record. The crucial and deeply unsettling question for us is, where is this filter located? Is it behind us, a challenge we have already miraculously overcome, or does it still lie ominously in our future? This is where the theory of panspermia interacts with the Fermi paradox in fascinating and contradictory ways. On one hand, panspermia could be seen as a mechanism that helps life bypass one potential great filter, the origin of life itself. Abiogenesis, the spontaneous emergence of life from non-living chemistry, might be an incredibly rare and difficult event. If comets and asteroids are routinely delivering prebiotic organics or even dormant microorganisms to young planets, they could be effectively seeding countless worlds, giving life a massive head start and making its initial appearance a common occurrence rather than a singular miracle. In this optimistic view, panspermia pushes the great filter further down the timeline. The galaxy might indeed be teeming with simple microbial life, but the filter that prevents it from advancing to intelligence could be a later developmental stage. But there is a much darker possibility. Panspermia itself could be a great filter. While the idea of life surviving a journey through space is plausible, the process of successfully colonizing a new world might be astronomically unlikely. Imagine a microbe hardy enough to survive the radiation and cold of an interstellar voyage, finally reaching a planet with liquid water and a suitable atmosphere. Its challenges are only beginning. It must land in a hospitable niche, activate from its dormant state, begin to replicate, and outcompete any native chemistry or biology. It must then navigate billions of years of evolutionary pressures without being wiped out by extinction-level events. The transition from a delivered seed to a stable, enduring biosphere might be the true bottleneck. The universe could be littered with the frozen, dormant remains of life that arrived but never quite managed to take root, making successful panspermia an exception rather than a rule. Other potential filters unrelated to panspermia could explain the silence. Perhaps the development of complex multicellular life is the true hurdle, an evolutionary leap that required such a precise and unlikely series of events that it has only happened once. Or maybe the filter is the emergence of technology and intelligence itself. It's possible that any sufficiently advanced civilization inevitably discovers the means of its own destruction, whether through nuclear war, environmental catastrophe, or a misstep with artificial intelligence, and silently extinguishes itself shortly after reaching a technological apex. The filter, in this case, is not behind us but waiting for us in the very near future. Another haunting solution to the paradox suggests that advanced civilizations are out there, but they are so profoundly different from us, existing in dimensions or scales we cannot perceive, that communication is impossible. Or perhaps they are choosing to remain silent, observing a form of cosmic quarantine to protect us or themselves from the dangers of contact. The universe might not be empty, but rather we are like ants in a vast jungle, unaware of the civilizations quietly existing all around us. The interplay between panspermia and the Fermi Paradox ultimately leaves us with a humbling duality. The theory offers a hopeful vision of a biologically connected galaxy where life is a constant spreading phenomenon. Yet the profound silence that greets our telescopes suggests that even if life is everywhere, its persistence and progression into something we would recognize are terrifyingly fragile. It forces us to look at our own planet not just as a possible recipient of life's seeds, but as a precious and perhaps rare example of an experiment that has, so far, succeeded against unimaginable odds. Our continued existence might not be a given, but an extraordinary and temporary victory in a cosmos that is either indifferent to life or filled with silent witnesses to its inevitable demise. But if the seeds of life were not just scattered by chance but planted with purpose, how would we ever know? The search for extraterrestrial intelligence has long been dominated by the hunt for radio signals, a quest for a cosmic hello. Yet, if an advanced civilization sought to propagate life, they might not bother with a message that would take millennia to arrive. They might leave their signature in life itself. This opens a breathtaking new frontier in our search, moving beyond traditional SETI to the hunt for technosignatures, evidence of technology, not in the form of a signal, but embedded in the very fabric of biology. Imagine a future where our telescopes, powerful enough to analyze the atmospheres of distant exoplanets in fine detail, discover something inexplicable. They might find a world with a biosphere that appears to be thriving, yet its chemical makeup defies all our models of natural evolution. Perhaps the ratio of certain gases is too perfect, too optimized for stability, suggesting an artificial manipulation of the planet's greenhouse effect to maintain habitable conditions. Or maybe we would detect the presence of complex organic molecules that are essential for life, but in combinations or isotopic patterns that simply do not occur in nature, like a specific, unnatural ratio of left-handed to right-handed amino acids that points toward bioengineering. These wouldn't be the simple building blocks we find on comets. They would be the finished product bearing the hallmarks of a designer. This search for artificial biosignatures forces us to reconsider what we're even looking for. A civilization capable of directed panspermia would possess a mastery of biology far beyond our own, potentially using synthetic biology to create microorganisms specifically designed to terraform worlds. These wouldn't just be hardy survivors, they could be engineered pioneers programmed to activate upon encountering water and a suitable atmosphere, rapidly processing a planet's chemistry to create a breathable atmosphere and lay the groundwork for more complex ecosystems. The evidence of this grand-scale gardening might be visible in the atmospheric composition of a young planet, an exoplanet that shows a rapid, geologically inexplicable shift from a toxic, high carbon dioxide atmosphere to an oxygen-rich one could be displaying the telltale signs of a seeded terraforming process, a technosignature of a cosmic greening project unfolding over millennia. The implications of such a discovery would be as profound as they are terrifying. Finding a radio signal would tell us that someone is out there. Finding evidence of artificial panspermia would suggest that someone has already been here, or at least that the spread of life is a conscious, technological act within the galaxy. It would mean that the tree of life we see on Earth might not be a wild, untamed forest, but a cultivated garden, and we could be the unawares descendants of a planting we never knew occurred. This shifts the entire paradigm of SETI from listening for a message to reading the cosmic landscape for the fingerprints of a gardener, a search for evidence not of a civilization's communication, but of its legacy, written not in stone or radio waves, but in the very DNA of world. This incredible power to reshape other worlds is no longer a distant science fiction fantasy. It is a tangible possibility sitting on our own technological horizon. As we stand at the precipice of becoming an interplanetary species, we are forced to confront a profound ethical dilemma. If we possess the capability to seed life on other worlds, do we have the right to do so? The concept of humanity becoming the deliberate agent of panspermia, of playing the role of cosmic gardener, is one of the most weighty responsibilities we have ever faced. The target for such an endeavor is clear: Mars with its thin atmosphere and frozen water ice, or Jupiter's moon Europa with its vast subsurface salty ocean, present themselves as the most promising candidates for terraforming. The proposed method is elegant in its simplicity. We would send spacecraft laden with specially engineered, incredibly hardy microorganisms, perhaps extremophiles similar to those we find on Earth, or entirely new synthetically designed life forms. These microbes would be selected for their ability to survive in harsh conditions and, crucially, for their capacity to perform specific functions, like metabolizing the Martian soil to release oxygen or breaking down compounds to thicken the atmosphere, slowly engineering a dead world into a living one over centuries. The potential benefits are undeniably alluring. Terraforming could offer a long-term survival strategy for humanity, a way to create a second genesis and ensure that the flame of life is not extinguished by a single catastrophe on Earth. It represents the ultimate expression of human ingenuity and our drive to explore and inhabit new frontiers. This ambitious vision transforms us from passive inhabitants of a single world into active shapers of our solar system, taking control of our cosmic destiny in a way that was once only the domain of gods. Yet this godlike power comes with a terrifying array of risks and ethical quandaries. The foremost concern is the irreversible contamination of a pristine alien environment. Mars and Europa are not merely barren rocks, they are entire worlds with their own unique chemistry and geology, and they may hold answers to the universe's deepest questions about the origin and distribution of life. By introducing earthly microbes, we could irrevocably destroy any nascent, undiscovered alien biology. Imagine the tragic irony of landing on Mars to search for life, only to realize we have already smothered it with our own, making it impossible to ever know if life arose there independently. This would be a loss of incalculable scientific and philosophical value, the destruction of a second genesis of life before we even had a chance to discover it. The principle of planetary protection, which currently guides our space exploration with strict sterilization protocols, exists precisely to prevent this catastrophic forward contamination. To deliberately violate this principle would be an act of unprecedented cosmic arrogance. Furthermore, we cannot predict the long-term consequences of such a massive biological intervention. Our engineered microbes might not behave as intended. They could mutate, outcompete each other, or interact with the alien environment in unpredictable ways, potentially creating a toxic, runaway ecological disaster instead of a paradise. We would be unleashing a self-replicating, evolving system onto a new world with no way to recall it. The responsibility we would bear for every subsequent change on that planet for billions of years is a burden almost too heavy to comprehend. This forces us to ask not only if we can do this, but whether we should. Do we, as a species still struggling to responsibly steward our own planet, possess the wisdom, the unity, and the long-term perspective to ethically manage the creation of an entire biosphere? The decision to seed another world is not just a scientific or engineering challenge. It is the ultimate test of our maturity as a civilization. It asks us to look beyond our immediate desires and consider our role in the cosmos not as conquerors, but as potential stewards in a universe that may be far more alive and far more fragile than we ever imagined. To truly test the limits of this incredible idea, we have to move beyond astronomical observation and theoretical models, bringing the question down to Earth into the controlled chaos of the laboratory. Scientists around the world are now constructing intricate experiments that physically simulate the violent conditions of a cometary impact, firing projectiles at astonishing speeds into targets that mimic a comet structure. These aren't simple simulations, they are hypervelocity impact tests using advanced equipment like two-stage light gas guns to accelerate tiny pellets to speeds exceeding 16,000 miles per hour. The goal is breathtakingly direct: to recreate for a fraction of a second in a lab the immense pressures and temperatures of a planetary collision and see what emerges from the other side. The design of these experiments is crucial to their success. Researchers don't just fire bullets at blocks of ice. They carefully construct their targets to be accurate analogues of a real comet's nucleus-porous mixtures of water ice, silicate dust, and complex organic compounds like amino acids or even simple sugars. In some landmark studies, scientists have gone a step further, embedding hardy microorganisms like the bacteria Rhodococcus erythropolis or the legendary tardigrade directly into these icy matrices. The projectile, often a small sphere of aluminum or sapphire, is then fired at this frozen test bed. Upon impact, sensors capture data in microseconds, measuring the incredible shock pressures and temperature spikes, while the resulting vapor and debris are meticulously collected for analysis. The results from these high-stakes laboratory collisions have been nothing short of revolutionary. They have shown that while the outer layers of the target are indeed vaporized instantly, material nestled deep within the core can be surprisingly protected. The porous, cushion-like structure of the ice-dust mixture acts as a shock absorber, significantly dampening the peak pressures experienced in the interior. Perhaps even more astonishingly, the analysis of the post-impact debris has repeatedly confirmed that a significant percentage of the complex organic molecules not only survive but remain chemically intact. The amino acids aren't shattered back into their constituent atoms, they come through the inferno still recognizable. When living microbes are included in the test, the findings are even more profound. A notable percentage of these tiny organisms survive the hypervelocity impact and, when placed in a nurturing environment, are able to recover, metabolize, and replicate. They withstand instantaneous pressures exceeding 1.14 gigapascals, that's over 1 million times the atmospheric pressure at sea level, a force far greater than anything found in the deepest ocean trenches. This experimental evidence provides the crucial, tangible link in the panspermia chain, demonstrating that the survival of both the ingredients for life and life itself is not just a theoretical possibility, but a physical reality under conditions that accurately mimic a comet's arrival on a new world. The search for answers is accelerating, moving from theoretical models and lab simulations to a new era of daring missions and breathtaking technological leaps. Our next chapter in this cosmic detective story will be written by a fleet of robotic explorers, each designed to probe the most promising corners of our solar system for the signs of life. Leading this charge is NASA's Dragonfly mission, an endeavor that sounds like it was pulled from the pages of science fiction. Slated to launch in 2028, Dragonfly is a revolutionary rotorcraft lander destined for Titan, Saturn's largest moon. Titan is a world that simultaneously feels alien and eerily familiar. It's shrouded in a thick, hazy atmosphere and possesses a complex hydrological cycle. But instead of water, it rains liquid methane that carves rivers and fills great lakes on its icy surface. This unique environment, rich in organic chemistry and potential energy sources, makes Titan a prime candidate for harboring life as we don't know it. Dragonfly will hop from one site to another, using its rotors to fly through Titan's dense atmosphere, analyzing the Moon's surface composition in multiple locations. Its suite of instruments will be specifically tuned to sniff out complex organic molecules and even look for potential chemical signatures that could indicate biological processes, offering our first direct look at prebiotic chemistry on a scale and complexity that may rival the early Earth. While Dragonfly explores the surface of a distant moon, our eyes on the cosmos are being fundamentally transformed by the James Webb Space Telescope. JWST is not just an incremental improvement, it is a paradigm shift in our ability to search for life's fingerprints across the galaxy. Its unprecedented infrared sensitivity and powerful spectrographs allow it to perform a feat that was once pure fantasy, analyzing the atmospheres of planets orbiting other stars known as exoplanets. As these distant worlds pass in front of their host stars, a tiny fraction of the starlight filters through their atmospheres. JWST can dissect this light, identifying the specific chemical signatures imprinted within it. The holy grail of this search is a combination of gases that cannot be easily explained by geology alone. A potential biosignature. The simultaneous presence of oxygen and methane, for instance, is a powerful candidate because these gases rapidly destroy each other unless they are being continuously replenished, potentially by living processes. JWST is already conducting these atmospheric forensics on rocky planets in the habitable zones of their stars, bringing us closer than ever to answering the question of whether we are alone in the universe, one spectrum at a time. Yet, for all the power of remote sensing, there is still no substitute for holding a piece of another world in our hands. This understanding is driving the ambitious push for sample return missions, the ultimate goal for planetary scientists. While the OSIRIS-REx mission has already returned a precious sample from the asteroid Bennu, the next frontier is even more tantalizing, bringing material back from a comet or an icy moon. Proposals are actively being developed for missions that would rendezvous with a pristine comet from the Kuiper belt, gently touch its surface, and collect a core sample from its icy interior before returning it to Earth in a meticulously sealed capsule. The scientific value of such an endeavor would be immeasurable. In our most advanced labs, free from the time and power constraints of miniaturized space-borne instruments, we could conduct a full forensic analysis of the comet's organic inventory, searching for the specific molecular patterns and isotopic ratios that could definitively point toward a biological origin. The most compelling target for a sample return, however, may be Europa, Jupiter's enigmatic ice-covered moon. The consensus is strong that beneath its cracked and icy crust lies a vast global saltwater ocean, potentially holding more than twice the water of all Earth's oceans combined. This subsurface sea is heated by the tidal forces of Jupiter's immense gravity, creating conditions that could be ideal for life. Future missions envision not just orbiting Europa, but landing on its surface, drilling or melting through the ice shell, and deploying a submersible to explore the alien ocean below. While a full return of a liquid water sample from the depths of Europa presents immense technical and planetary protection challenges, it represents the culmination of this entire quest. To one day analyze water that has been isolated from the surface of the solar system for billions of years, and to see within it not just the building blocks of life, but perhaps life itself, would be the ultimate validation of the idea that we live in a living cosmos, seeded and connected by these silent, icy travelers. For all its compelling possibilities, the theory of cometary panspermia is not without its formidable detractors. A truly balanced view requires us to engage seriously with the powerful scientific criticisms that challenge this captivating idea, because a hypothesis is only as strong as its ability to withstand scrutiny. One of the most significant hurdles is the profoundly hostile radiation environment of space. During an interstellar voyage lasting millions of years, any potential biological passenger would be subjected to a constant, relentless bath of cosmic rays and high-energy particles from solar flares. This radiation doesn't just pass through, it can shred DNA, break apart complex organic molecules, and effectively sterilize anything not incredibly well shielded. While we know extremophiles on Earth are radiation-resistant, the doses accumulated over such astronomical timescales are of a completely different magnitude. Proponents argue that a microbe buried deep within several meters of a comet's icy and rocky matrix could be protected, acting as a natural radiation shield. But critics counter that we simply don't have enough data to confirm that any known organism could survive that specific long-term onslaught. Another major point of contention is the sheer statistical unlikelihood of the entire process, which critics often describe as a series of cosmic near-miracles. For panspermia to work, a life-bearing fragment must first be ejected from its home world by a massive impact, but not so massive that it vaporizes everything. This fragment must then achieve escape velocity from its star system, a feat requiring a precise gravitational slingshot. It must then survive the vacuum, cold, and radiation of interstellar space for an immense duration. Next, it must somehow encounter another star system and be captured by its gravity rather than just sailing through. Finally, it must collide with a planet in that system that not only is habitable but is habitable at that exact moment in its geological history, and the impact must be gentle enough that the payload isn't destroyed. Skeptics argue that the probability of this entire chain of events succeeding is so infinitesimally small that, while it might happen on rare occasions, it cannot be considered a primary mechanism for the spread of life in the galaxy. The universe may be vast, they say, but it is also overwhelmingly empty, making these kinds of successful transfers more of a theoretical curiosity than a driving force in biology. Perhaps the most philosophically weighty criticism is that panspermia, in its simplest form, doesn't actually solve the fundamental mystery, it merely relocates it. This is often called the begging the question objection. If we argue that life on Earth was seeded by a comet from another world, we are still left with the exact same profound question: how did life originate on that world? All we've done is push the problem of abiogenesis, the leap from non-living chemistry to a living, self-replicating system, onto another planet, or perhaps even another star system. We haven't explained the mechanism, we've just moved it farther away, making it even harder for us to study. Critics contend that this is a classic example of avoiding a difficult scientific problem rather than addressing it head-on. The real scientific challenge, they argue, is to understand how abiogenesis occurs under natural planetary conditions, not to invoke an extraterrestrial deus ex machina that simply postpones the need for an explanation. However, advocates for the theory offer thoughtful counterarguments to each of these points. Regarding radiation, they point to experiments showing that certain bacteria and tardigrades can indeed survive astonishingly high doses, and that the mineral content within comets and asteroids could provide more than enough shielding for dormant organisms. To the statistical argument, they invoke the mind-boggling scale of the cosmos. With hundreds of billions of stars in our galaxy alone, each with its own planetary system and countless trillions of comets, the law of truly large numbers suggests that even wildly improbable events will happen eventually. What seems like a 1 in a trillion long shot might actually occur millions of times across the galaxy. And to the charge of simply moving the problem, many panspermia supporters clarify that they are not trying to explain the ultimate origin of life itself. Instead, they see it as a theory about the distribution of life. Their point is that if abiogenesis is an incredibly rare event, occurring maybe only once in an entire galaxy, then panspermia becomes the crucial mechanism that spreads the results of that one incredible event to countless other worlds, making a galaxy that had only one genesis appear to be teeming with life. In this view, panspermia doesn't replace abiogenesis, it amplifies its consequences, turning a single spark into a potential galactic wildfire. This ongoing debate is not a weakness of the idea, but rather its greatest strength, driving the scientific process forward as we gather more evidence from missions to comets, asteroids, and the distant moons of our own solar system. While the scientific debate around panspermia continues in laboratories and academic journals, the idea has already achieved a remarkable victory in the realm of the human imagination, taking root in our stories and myths. Science fiction has long served as a cultural playground for exploring the profound implications of scientific theories, and panspermia has provided a fantastically rich soil from which some of the genre's most enduring narratives have grown. These stories have done more than just entertain. They have fundamentally shaped how the public perceives this cosmic possibility, often blending the lines between hard science and philosophical speculation into something truly compelling. One of the earliest and most influential treatments came from the visionary author Arthur C. Clarke. In his seminal work 2001, A Space Odyssey, developed concurrently with Stanley Kubrick's iconic film, Clarke presented a version of directed panspermia that was both awe-inspiring and chillingly impersonal. The mysterious black monoliths that appear throughout human history are revealed to be tools of an advanced alien intelligence designed to nudge evolution along a specific path. In the novel's opening act, a monolith confronts a band of our primitive ancestors, somehow unlocking the cognitive leap toward tool use and violence. This was not a gentle delivery of microbes, but a deliberate intervention in the development of an entire species. Clarke reframed panspermia not as the seeding of life's ingredients, but as the seeding of intelligence itself, suggesting that our entire evolutionary trajectory might have been a carefully orchestrated program run by unseen galactic gardeners. This narrative imprinted a powerful image on the public consciousness, the idea that our origins might be tied to a purposeful yet utterly enigmatic external force. Clarke returned to this theme with even greater depth in his novel Rendezvous with Rama. Here, the concept is stripped of direct intervention and presented as a breathtakingly grand and neutral process. The massive, cylindrical starship Rama that enters our solar system is not a warship or a colony vessel. It is a self-contained world, a celestial ark utterly indifferent to the humanity that scrambles to explore it. Its purpose seems to be pure preservation and transportation. It carries within it a vast collection of flora and fauna from some distant star, frozen in time, waiting to be revived in a new solar system. Rama presents panspermia as a natural, almost mechanical function of a mature galactic civilization, a kind of cosmic biodiversity project operating on a million-year timescale. This portrayal captured the theory's potential scale and majesty, suggesting that the universe might be crisscrossed with such silent, automated gardeners, ensuring the survival and distribution of life without any need for direct contact. Moving from the cerebral to the visceral, the horror genre has also seized upon panspermia, exploiting its most terrifying implication, that what arrives from the stars might not be a benevolent gift. The Alien franchise is perhaps the most potent example of this dark twist. The infamous xenomorph embodies a kind of malignant biological panspermia. Its reproductive cycle is a nightmare of parasitic invasion, using living hosts to propagate its kind. The derelict spacecraft found on LV-426 in the first film acts as a grotesque parallel to Clarke's Rama, another alien ship carrying cargo, but this time a cargo of pure destruction, a biological weapon that turns the very concept of life seeding into a horrifying contagion. This narrative thread plays on deep-seated fears of infection and the unknown, framing the cosmos not as a nurturing garden but as a dark forest filled with predatory biology waiting to find a new host planet. In more recent years, stories have attempted to bridge the gap between the scientific and the speculative. Films like Prometheus and its sequel Alien, Covenant explicitly grapple with the idea of humanity's creators being an alien species, the engineers, who seeded Earth with their own DNA. While these films lean into grand mythology, they nonetheless bring the question of our engineered origins to a mass audience. Conversely, a film like Arrival approaches the idea from a more linguistic and philosophical angle, exploring how communication with truly alien life would force us to reconsider our own place in a universe that might be biologically interconnected in ways we are only beginning to perceive. The collective impact of these stories on public perception is immense. They have provided a shared vocabulary and a set of powerful visual metaphors, the monolith, the derelict ship, the alien spore, that allow us to grapple with a theory that is otherwise abstract and data-driven. Science fiction has given panspermia a narrative heartbeat, transforming it from a dry hypothesis into a canvas for exploring our deepest hopes and fears about the cosmos. It allows us to ask in a deeply personal way whether we are orphans in a silent universe, the beloved children of star-faring creators, or merely the temporary hosts for a biology that cares nothing for us. These stories haven't proven the theory, but they have ensured that its questions resonate far beyond the pages of scientific journals, making the search for our cosmic origins one of the most enduring and human of all quests. Accepting the possibility that life on Earth may have extraterrestrial origins forces a seismic shift in our collective self-perception, challenging the very core of human identity and our place in the grand scheme of the universe. For centuries, the prevailing narrative has been one of terrestrial exceptionalism, the comforting idea that our planet is a unique oasis of life, a singular, miraculous accident in an otherwise silent and empty void. This view placed humanity at the center of a biological story that began and perhaps would end here. But if panspermia is validated, that story is completely rewritten. We are no longer the isolated protagonists of a solitary drama on a lone world. We become part of a sprawling, interconnected cosmic epic, a single chapter in a biography that spans light years and encompasses countless stars. This realization is profoundly humbling, displacing us from the center of the biological universe and recasting us as one thread in a vast galactic tapestry of life. This shift from a geocentric to a cosmocentric view of biology carries immense weight for our understanding of life's significance. If life can travel between worlds, then it ceases to be a rare and fragile anomaly. Instead, it becomes a robust, persistent, and perhaps even inevitable property of matter under the right conditions, a fundamental feature of the cosmos, as intrinsic to its workings as gravity or nuclear fusion. Life, in this view, is not something that happens on a planet, but something that happens to a planet, an active process that spreads and evolves across stellar distances. This transforms the universe from a cold, mechanical clockwork into a potentially living, breathing entity, a place where biology is woven into the fabric of space itself. The question changes from "are we alone?" to "how are we related?" Our search for extraterrestrial life becomes less about finding strangers and more about finding long-lost cousins, perhaps separated from us by billions of years of independent evolution but sharing a common cosmic ancestry. Such a paradigm shift would inevitably ripple through our philosophical and even theological frameworks. Many earthly religions and belief systems are deeply rooted in the special relationship between a creator and humanity, often with our planet depicted as a chosen creation. The discovery that our genesis might have been a natural, astronomical process, a delivery of prebiotic material or even dormant organisms, does not necessarily negate the idea of a creator, but it certainly expands the canvas upon which that creation is painted to an almost unimaginable scale. It invites a theology of immense grandeur, where divine action operates on a galactic scale over billions of years, using comets and asteroids as its brushes. Conversely, for a secular worldview, it offers a new origin story that is no less awe-inspiring, one where the laws of physics and chemistry conspire to ensure that life, once it arises, has a mechanism to perpetuate and distribute itself, making the universe inherently bio-friendly. On a more practical level, this knowledge would fundamentally alter the meaning of the word Earthling. If we are the product of cosmic ancestry, then our kinship extends beyond the borders of our atmosphere. Every living thing on this planet would share not just a common ancestor in a primordial pond, but a common origin on some distant, unknown world, or perhaps in the icy heart of a comet that formed before our sun even ignited. This shared extraterrestrial heritage could foster a profound sense of planetary unity, a collective identity that transcends national, ethnic, and species boundaries. We are all truly made of star stuff, and if that star stuff was pre-packaged with the instructions for life, it binds every blade of grass, every microbe, and every human into a single family with a truly universal pedigree. This perspective could be the ultimate catalyst for a new global ethic, one grounded in the understanding that we are all crew members on spaceship Earth, entrusted with the care of a biological legacy that we did not create alone, but inherited from the cosmos itself. Perhaps the most elegant and compelling solution to this great mystery is not to choose one theory over the other, but to see them as two essential chapters in the same extraordinary story, a cosmic relay race where one process hands the baton to the next. This hybrid model elegantly merges the strengths of both ideas while sidestepping their individual weaknesses, painting a picture of our origins that is both grand in scale and specific in its planetary details. Imagine the early Earth not as a blank slate, but as a construction site that received a massive, pre-ordered delivery of the most critical and difficult to manufacture materials. The comets and asteroids during the late Heavy Bombardment were those delivery trucks crashing into the planet and unpacking their precious cargo of water, amino acids, nucleobases, and phosphorus. This wasn't just a random assortment of chemicals, it was a concentrated infusion of the very compounds that are notoriously challenging to form in large quantities on a planetary surface. This delivery gave our planet a monumental head start, effectively solving the problem of sourcing the raw ingredients. But having the ingredients is one thing, knowing what to bake with them is another. This is where the established principles of abiogenesis come into play, taking over the narrative in Earth's uniquely favorable kitchen. Our planet provided the perfect conditions for the next step. A stable environment with vast, warm, shallow oceans, tidal pools that concentrated these molecules, and energy sources like geothermal heat and lightning to drive their reactions. The theory of abiogenesis doesn't have to explain the spontaneous generation of incredibly complex molecules from nothing. Instead, it can focus on the more plausible task of organizing and assembling these pre-delivered building blocks. The transition from non-living chemistry to a living, self-replicating system remains a monumental leap, but it becomes a far more achievable one when you begin with a rich, concentrated broth of the right starting materials. The complex pathway from molecules to a primitive protocell is still shrouded in mystery, but it's a mystery that becomes infinitely easier to solve when the most difficult steps of molecular synthesis have already been handled by the chemistry of interstellar space and the frozen interiors of comets. This unified view is not just a convenient compromise, it's a framework that is actively supported by a growing body of evidence. The discoveries from missions like Stardust and Rosetta prove that the delivery of organics was not only possible but factually occurred. Meanwhile, laboratory experiments on Earth continue to make progress in understanding how those delivered molecules could self-organize under realistic early Earth conditions. Scientists have successfully created membrane-bound vesicles that can trap nucleic acids and even exhibit primitive metabolism, all using nothing more than the types of fatty acids and other compounds known to exist on comets and meteorites. The hybrid model doesn't ask us to believe in two miracles. It asks us to see one continuous cosmic process where the universe handles the large-scale production and distribution, and individual planets handle the final local assembly. It suggests that while the specific recipe for life might be unique to each world, the grocery list of ingredients is universal, written into the very laws of physics and chemistry, and delivered by the silent, patient gardeners of the cosmos. So where does this leave us in this grand cosmic detective story? The evidence, when we piece it all together, builds a strikingly compelling case. We now know, thanks to missions like Stardust and Rosetta, that comets are veritable treasure chests of prebiotic material, carrying within their icy hearts water, amino acids like glycine, sugars, and even the vital phosphorus needed for DNA. We understand that the harsh conditions of space are not an absolute barrier, as the incredible resilience of Earth's own extremophiles and the results of hypervelocity impact experiments prove that survival is not just possible but plausible. The chemistry that creates these building blocks isn't a rare planetary phenomenon. It's a fundamental process occurring in the vast molecular clouds between stars, with comets acting as the natural preservation and distribution system for these organic riches across young solar systems. The timeline of life's rapid appearance on a once molten Earth fits perfectly with the cataclysmic yet creative period of the late Heavy Bombardment, where these icy messengers may have delivered the very ingredients that allowed biology to gain a foothold with astonishing speed. Yet, for all this compelling evidence, profound mysteries remain. We still do not know how that monumental leap from complex chemistry to a self-replicating living system actually occurs. The panspermia hypothesis, in its various forms, offers a powerful framework for how the ingredients were delivered, but the recipe for life itself, the instructions for baking the cake, is a secret we have yet to fully unlock. The question of whether we are the product of a random, natural process or something more directed still hangs in the void, awaiting more data. And the haunting silence of the Fermi Paradox reminds us that even if life is widespread, its progression to intelligence and longevity may be fraught with filters we are only beginning to comprehend. This is not the end of the story, it is a thrilling new beginning. We are living in a golden age of exploration, where every new mission from the rotorcraft on Titan to the atmospheric sleuthing of the James Webb Space Telescope brings us closer to answering these ultimate questions. The quest to understand our cosmic origins is one of the most profound journeys humanity has ever undertaken, a drive to find our place in a vast and interconnected universe. It is a story written in the frozen code of comets, in the chemistry of distant stars, and in our own unyielding curiosity. So the next time you look up at a dark, clear night sky, remember that those silent points of light are not just distant suns. They are potential homes, way stations in a great galactic exchange of life's seeds. Stay curious, follow the discoveries as they unfold, and never stop wondering about the incredible possibility that we are all citizens of a much larger living cosmos.